As we stand on the brink of the 6G era, the demands on our wireless infrastructure are reaching unprecedented levels. Traditional communication techniques are reaching their physical limits, struggling to meet the needs for higher capacity and ultra-low latency. With billions of devices connecting in increasingly complex scenarios, we need a new paradigm for intelligent communication. Enter Generative Adversarial Networks, or GANs, a powerful AI framework that is revolutionizing how we design wireless systems. At its heart, a GAN consists of two competing neural networks, the generator and the discriminator. The generator's job is to create synthetic data that looks indistinguishable from real-world communication signals. The discriminator acts as a judge, constantly trying to tell the difference between the real data and the synthetic samples. Through this adversarial process, both networks improve until the generator can replicate complex data distributions with incredible accuracy. The first major role for GANs in the 6G landscape is data generation and augmentation. In environments like underwater or high-mobility scenarios, collecting real-world data is often too expensive or physically impossible. GANs can learn the characteristics of these complex channels and generate large volumes of synthetic data for testing and design. This is particularly vital for underwater optical communications, where traditional modeling often falls short of reality. By augmenting limited datasets, GANs allow us to train more robust communication systems without the need for exhaustive field trials. This becomes even more critical as we move toward massive MIMO systems with hundreds of antennas. GANs also enable spectrum augmentation, helping devices adapt to rapidly changing interference and traffic patterns. They can simulate various types of interference, allowing us to build receivers that can survive in the noisy 6G environment. The second pillar of GAN integration is performance optimization of the communication link itself. In 6G, providing feedback on channel state information can create a massive overhead, consuming precious bandwidth. GAN-based compression modules can drastically reduce this overhead, learning to transmit only the most essential information. Similarly, for channel estimation, GANs can reconstruct high-dimensional channel matrices with far fewer pilot signals. This reduction in complexity translates directly into lower power consumption for both devices and infrastructure. For massive MIMO, where traditional methods struggle with scale, GANs offer a pathway to truly efficient beamforming. They can recover information from sparse signals without the rigid mathematical constraints of traditional methods. This enables real-time, adaptive beamforming that can keep up with the extreme mobility expected in the next decade. By offloading complex computations to optimized neural networks, we can finally reach the ultra-low latency goals of 6G. The third transformative role for GANs is in the domain of signal classification and recognition. In the crowded 6G spectrum, identifying specific signal types amidst massive interference is a major challenge. GANs enable semi-supervised learning, using a small amount of labeled data to make sense of a vast ocean of unlabeled signals. Hybrid GAN structures can classify signals while simultaneously improving the overall robustness of the detection network. This is vital for automatic modulation recognition, allowing receivers to adapt to the transmitter's settings instantly. By accurately classifying interference, systems can take proactive steps to mitigate its impact on performance. These GAN-enhanced classifiers are far more resilient to noise and environmental changes than traditional hand-coded features. This also opens new doors for physical layer security, identifying unauthorized emitters with high precision. While the potential is enormous, several research challenges remain before GANs can be fully deployed in 6G. Ensuring training stability and preventing mode collapse is a critical focus for current AI researchers. We must also optimize these models to run efficiently on the edge devices that will populate the 6G ecosystem. Modeling the joint correlation of signals across time, frequency, and space domains is the next big frontier. Developing unified performance metrics and standardization will be essential for industry-wide adoption. Ultimately, GANs are a key building block for truly AI-native networks that learn and evolve on their own. These networks will adapt in real time to every change in the environment, from weather patterns to user density. They will bridge the gap between theoretical models and the messy, unpredictable reality of the physical world. Collaborative AI systems will allow different parts of the network to share insights and optimize together. This will ensure the extreme reliability required for applications like remote surgery and autonomous transport. As 6G connects everything, GANs will provide the intelligence needed to manage this hyper-connected world. They act as a catalyst for innovation, breaking the bottlenecks of traditional communication theory. A new era of intelligent wireless communication is beginning, powered by generative AI. From deep-sea sensors to low-Earth orbit satellites, the reach of 6G will be universal. The future of wireless isn't just about faster speeds, it's about deeper intelligence. By embracing the power of GANs, we are building a more connected, efficient, and intelligent world. Stay tuned as we continue to explore the frontiers of technology and the future of connectivity.